discuss about traveling salesman problem using simulated annealing technique. So I will write briefly the steps involved in simulating algorithm. First step is generate randomly the initial solution. So we have already discussed the simulated annealing algorithm in the previous videos. So I am writing directly initial solution x naught and compute the objective function f of x naught. In the second step, so you need to start with initial solution, that is the first step, and then once you got initial solution, you have to generate the neighboring solution of the initial solution. So generate new solution which you can call it as x new. Okay, x new. Here also you can turn as x capital X naught. This is x new. So followed by, you can compute or calculate the fitness function, objective function, by substituting x new in f of x. So third step is, what you have to do is, you have to compute the difference, which you will call it as delta f of x new minus f of x naught. So you need to find out the difference between the fitness values of new solution and old solution. Okay, so that is the meaning here. And now what you have to do is, you have to compare. If the delta f is less than or equal to 0, what you have to do? So let us suppose we are going to, here in this traveling salesman problem, our job is to find the minimum path, okay, minimum path length. So therefore it is a minimization problem. Okay, so if the difference between the fitness value of new solution and old solution is less than or equal to 0, then you can happily accept the new solution. So in the fifth step, what you will do is, you accept the new solution. Accept the new solution. So that means what you will do means, so you will assign something like this. So let you transform the x new into x naught, and then simultaneously the f of x naught value, old value is replaced with new value, okay, new fitness value. So that step we have to do. And the next step is, say for example, what happens if delta f is greater than 0? So that means you have to write if. So what if the new solutions, the performance of the new solution is not good, is not better than the old solution? Means you have to go for, you have to perform the you have to calculate the Metropolis rule. Calculate, or you can see, you cannot directly ignore the new solution. What we will do means, we will accept new solution. That means here, what is the new solution? X new, based on Metropolis rule. So let us see what is Metropolis rule here. In the, what is Metropolis rule? Metropolis Rule. So what is Metropolis Rule? Yes. So you will calculate, you will take a random sample, you will take a random value between 0 to 1 from uniform distribution function, okay, and then you will calculate the exponential, you will perform the calculation like this. Say for example, result output capital O is equal to exponential of delta or delta f, or you can say as a here you can see we have calculated the difference in fitness function. So delta f by t for simplicity, okay, delta f by t. And so what we will do means, if the sampled value r is less than the output of the exponential function, here this is your exponential function, what we will do means we will take that new solution. That means then what we will do is, then we will accept the new solution. X new is accepted, and simultaneously its value is also, the fitness value is also replaced. If the sample value is greater than 0 means you ignore the new solution. So that is a specialty. So what we will do is, we will take a random sample between 0 to 1 and then you will calculate the exponential function, okay, which is dependent on capital T. So if r is less than 0, you accept the solution, new solution. If r is greater than 0, you will not accept the new solution, that means you will ignore. So after that, once you calculated the function, you have to check whether we reached number of iterations, maximum number of iterations or not, okay. Check whether maximum number of iterations is reached or not, is reached. Or I will write in another way also, if maximum number of iterations are reached, if the maximum number of iterations are reached, then what we will do means we will check if this condition is false. I will write in other way also, so that you will understand in a better way. If maximum number of iterations is not reached, then 11th step, then go to step, that is a go to step, again you have to generate new solution. So I think you have to go to step 2, Similarly, else, then what you have to do means, that means if the number of iterations, maximum number of iterations is reached, then again you have to check if the maximum temperature is reached or not. Okay, if maximum temperature is not reached, if maximum temperature is not reached, if maximum number of temperature is not reached, then what we will do means you will perform this operation. You will decrease the temperature with some constant. Okay, and then you have to go to step 2. Okay, that means for each temperature you will perform n number of maximum number of iterations. Okay, else that means if maximum temperature is reached, else if maximum temperature is reached, then you can stop the process, then you can break the loop, and return the optimal value. Okay, you can return the optimal solution. This is how the algorithm will work. Here you need to supply the different parameters. So what are the parameters you have to specify? How many number of iterations, that means maximum number of iterations, and the capital T, that is important. So this is a rough view of the steps involved in simulated annealing technique. Now Once we understood this, we will try to solve the TSP problem, Travelling Salesman Problem. So let us see the Travelling Salesman Problem. In the previous class we have introduced about the Travelling Salesman Problem. So you can go through this. The Travelling Salesman Problem consists of a salesman and a set of cities. The salesman has to visit each one of the cities, starting from a certain town and returning to the same city. So here the challenge is you need to find the optimal length of the path. So that each city has to be visited only once by the traveling salesman person. Okay. So let us see, for this diagram, let us draw neatly. So we are having 5 cities. So I am writing in numerical form 1, since we are having 5 cities, let us label each city with numerical form. A as 1, B as 2, and C as 3, and D as 4, and E as 5. Okay, E as 5. Now the thing is, you need to fix the parameters in simulated annealing. Okay, in simulated annealing we have to fix the parameters. So what is the maximum number of iterations? Maximum number of iterations is, let us say 10 or 100. Okay, and the temperature is, maximum temperature is 10 degrees. So for each temperature you need to run 100 iterations. So this is the iterations. So let us draw the diagram first. 1, this is a graphical representation. 1, 2, 3, 4, 5 cities are there, and whenever there is a path, you can draw the edges, and the number on the edge represents the length, path length. And the distance between 1 and 4 is, in the problem it is given as 3, and here the distance between 3 and 5 is 3. Okay, so for simplicity, I am assuming additional edges also between the cities, so that we will get some, we can get some other useful solution. Let us say the distance between 1 and 3 is 5. Okay, similarly in between 2 and 5 is 6. Okay, so let us see the source here. What is the source? I assumed source is 1 and the destination is also 1. Okay, destination is also 1. The traveling salesman has to find the optimal path starting from first city and ending with the same city. So the paths in simulated annealing algorithm, you need to represent the features effectively. So here also we will represent like this. So one of the solution is you can represent like this. So 1, 2, 4, 5, 3, 4, 5, 1. So this is one such path. Okay. So for simplicity, you need not specify this source and destination again and again. So you can omit this source and destination. So this is the path. This is one such path, randomly generated path, 2, 4, 5, 3. Okay, 2, 4, 5, 3. Okay, 2, 4, 5, 3. Similarly, you can generate randomly 4, 5, 3, 2 also. Okay, so you need to find the randomly generated optimal path using simulated annealing technique. Let us see. We will see one algorithm. So as of now, this is how the features are represented. And another important thing is, if you see our algorithm, you can see the step 2. What is the step 2? Generate new solutions. So in the previous classes, we have seen how neighboring solutions are generated with the help of current solution. We have performed the step function, and we have drawn some random sample, and we have added to that current solution to get new solution. But in TSP problem, it is not like that. All are integers, so they are not real valued. Are understanding? So all are integers. So what you have to do is, you can define one type of new type of generating solution. So how to generate new solution? How to generate? Let us define one function. Generate new solution. New solution. So for that, in the previous video, we have discussed the mutation function for generic algorithm. So what we will do is, we will try to use the mutation what we have used in generic algorithm. That function we will try to use here also. Okay, we will use here. The specialty is, for simplifying, we are going to use mutation function as generating neighboring function to generate a neighboring solution. Okay, to generate neighboring solution. Okay, so let us recap what type of mutation function we have studied and what we are going to use. We will use a simple technique, exchange type mutation. Exchange type mutation. Say for example, if you are having one path like something like this, 4, 5, 3, 2. So you want to perform mutation. So the output will be, you randomly select any two positions, one first position and third position. So the output will be, just you need to exchange the values in the corresponding position. So 3 gets swapped to this, and 5 will be as it is, and 4 gets swapped, and 2. So this is your new child. So we are going to use the exchange type mutation for generating neighboring solutions in the simulated annealing technique. Okay. So let us see. By using this mutation technique, let us see how we will solve the problem. So in the simulating any algorithm, two important things are how the features are represented, how the neighboring solutions are generated given current solution. If this is the current solution, we can generate a neighboring solution using mutation technique. We have used mutation technique to generate neighboring solutions. Okay. So let us see what we can do. So once we understood this, let us draw a table. So I am going to show you only one iteration. So let us say serial number, or you can say first iteration number, this is the first iteration. So if you observe this program, that is algorithm, what is the first thing you need? You need to generate randomly initial solution. So x0 you need to perform. So current solution, you can take it as a x0. So you need to, since it is a first iteration, you randomly generate any path. Let us say for example 4532 is the generated path. 4532, that is a generated path or solution. And once just we are following the same simulated annealing algorithm steps. After that, your next thing is generate new solution. Okay. So here you need to compute initial solution, that means current solution, and its corresponding objective function also. So here the objective function for traveling salesman problem is, it is a sum of edges along the path. So for 4532, so please 4532, can you calculate? So you can see this 4532 means just sum up all the paths, sum up all the edge paths along this path. So 4 means it is a 12 plus 4, it is 22, 10, 22, and then plus 3, 25 again 2, 25 2 means 25, 4, 25 plus 4, 29 plus 2, 31. So therefore 31. Okay. So we got the fitness value of the current solution is 31. Just we have calculated the sum of length of paths. Okay. So next thing is, as per the algorithm, generate new solution. So I already told you, new solution is, you can see the algorithm, we are going to use mutation function for generating neighboring solution. Okay, so I am taking this, and then I am taking the first position and the third position and swapping. So to get new solution, so you will get something like this: 3, 5, 3, 5, 4, 2. So this is the new solution I got. Once I got the new solution, you immediately calculate the fitness value. Okay, so f of x neo. So let us calculate this. Go to the graphical structure 3542. 3542. Please write it 3542. So from 1 to 3 here, 1 to 3, it is 5, 5 plus 3, 8, 8 plus 10, 18, 18 plus 8, 26, 26 plus 2, 30. Okay, 26 plus 2, 30. So therefore, the fitness value is 30. Okay. And the next thing is, what you have to do means, we have calculated the f of x neo. So as per the algorithm, next step is calculate the delta f. Calculate the delta f. So you can make another column, delta f. Delta f is difference between x new and x naught. So x new and x naught is clearly 30 minus 31. So 30 minus 31, that means minus 1. So just as per the algorithm only, we are making the columns. Okay, we are making the columns. You can see this. The next step is neighboring solution. 1 minute. So instead of a new solution, what I will do is I rename the new solution as neighboring solution. It will be better, and you can write here. Okay, we will write like this only, new solution. So what we will do is, the next step is, as per the algorithm, we have calculated the delta f. So next step is, delta f is clearly, it is less than or equal to 0. That means the new solution, that means a new path is better than the old path, or new path is better than the current path. So what you have to do is, as per this algorithm, you need to accept. Okay. So since you need to accept, what we will do is, you change. So in the second iteration, you need to accept. Okay. So here you can write as comment something like this, so that you will understand. Accept new solution. So that is a comment here in the first iteration. So what we will do is, we will take this new solution and we will add it to the current solution. So you change here 3, 5, 4, 2, and its corresponding fitness value is 30. So now with 3, 5, 4, 2, you try to generate a new neighboring solution. So again, go to the figure 3, 5, 4, 2. 3, 5, 4, 2 means this one only. So with this, try to generate new solution. You randomly take any two position and try to perform the mutation. 3, 3, 4, 5, 2. Instead of 3, 5, 4, 2, 3, 4, 5, 2. Now it is 3, 4, 5, 2. 3, 4, 5, 2 is the new neighboring solution. Let us calculate the fitness value of the new solution. 3, 4, 5, 2 means, let us calculate. 3, 4, 5, 2 means 1, 3 means 5. 5 plus 3, 8 plus 10, 18, 18 plus 6, 24, 24 plus 2, 24 plus 2, 26. Okay, 26 we got. So that means again the fitness value of the new solution is again it is better. If you calculate the difference between these two, you will get -4. So as per this algorithm, so I want to run this algorithm or show this iteration until the execution of Metropolis, so that you will have a better idea about what is happening. Okay. Luckily this time also we got a better solution, that is -4 means is less than or equal to 0. So what we will do means we will accept new solution. Therefore this solution is accepted. In the third iteration we will take this new solution as a current solution 3, 4, 5, 2 and its corresponding fitness value is 26. Now again with 3, 4, 5, 2 you try to generate a new neighboring solution. Again go to the figure. What is the path? 3, 4, 5, 2 was with 3, 4, 5, 2, that means 3, 4, 5, 2. Let us generate a new neighboring solutions. I am selecting these two. Okay, these two positions I am trying to exchange these two, 3, 4, 2, 5. So after randomly generating, I am getting something like this 3, 4, 2, 5. Let us calculate the fitness value of 3, 4, 2, 5. 3, 4, 2, 5 means what is the fitness value? Just you have to sum up the edge cost along all the paths. Okay, 3, 4, 2, 5 means 1, 3, 5, 5 plus 3, 8, 8 plus 8, 16, 16 plus 6, 22, 22 plus 5, 22 plus 5, it is 27. Now we got 27. Okay, now you can see the fitness value of the new solution is greater. That means the delta F is +1. That means the condition is violated. You can see this. So now what we will do means, here the delta F is greater than 0. So if delta F is greater than 0, we will not simply ignore the new solution. That means we will not simply ignore this path. Instead of the ignoring directly, we will ignore based on the Metropolis rule. Okay, Metropolis rule. As per the Metropolis rule, what we will do means, you add another column, that is R. R is a sampled value between 0 to 1. Okay, that is a 1. And another thing is, next thing is you have to calculate the exponential of delta F. You calculate O parameter, exponential of delta F by capital T. Let us assume the capital T, I already told you capital T is 10 degrees. So you can see my previous slide. So let us add another column. So let us add another column. Let us sample a value between 0 to 1. Let us say it is say for example it is 0.2. Okay, we randomly sampled between 0 to 1, we got 0.2. Now let us calculate the exponential of delta F by T. So you can clearly see exponential, you take the scientific calculator, so you can easily calculate the exponential of delta F. Delta F is there, 1 by 10 is exponential of 0.1. So I already took that in the website, online calculator, exponential of 0.1. So what is the value you got? 1.1. So let us see 1 minute. Again we will see exponential of minus 0.1, 0.9. Okay, so a small correction, instead of delta F, you calculate exponential of minus del of t. So what we got is, so what is the exponential value got? Minus 0.9. So 0.9 means, so you got here 0.9. Now you have to decide. So if you clearly see, as per the program, here you can see r is clearly less than 0. If r is less than 0, you need to accept the new solution. If r is greater than 0, you need to ignore. So here r is clearly less than O. So that means 0.2 is less than 0.9. So what we will do means, here we will accept new solution. Okay, new solution means in the fourth iteration, one minute. We will write something like this. We will accept the new solution. Here clearly, as per the algorithm, r is less than 0.9. So you take this new solution, 3, 4, 2, 5. So, and again you take the, even though you can see the fitness value is not better than the current solution we are taking because of this Metropolis rule. So that is a specialty. So in this way, the algorithm will run for n iterations. So if you see this, you can add another parameter also, capital T parameter. Okay, T means for all these iterations, initial value is 10. Okay, initial value is 10. So when you reach the iteration 100, what you will do means, you will decrease the temperature. Okay, that means 9. Again you have to run the algorithm. So again, for each temperature you have to run the algorithm 1, 2, 3 up to 100 times. For all the 100 times, you will put 9, temperature 9. So after reaching the 100th iteration, again you decrease the temperature. So finally, whatever the solution you got in the as a current solution, that is your optimum solution. Okay, that is your optimum solution. So this is how the algorithm works. So you need to have understanding of basic steps involved in simulating algorithm, and then you can solve the TSP problem using simulated annealing algorithm. Okay students, I have shown you for 4 iterations. You can continue for a number of iterations also. Thank you students.